Hi everyone, my name is John Doherty, and in today's video I'm going to be showing you how to deploy your Django and Celery project onto a Kubernetes cluster. So it doesn't really matter where this Kubernetes cluster is running. It could be running on AWS, DigitalOcean. It's all fairly standard across all those different cloud providers, which is great and should work across them all. In this video we'll be covering quite a lot of different topics such as continuous integration, continuous deployment, deploying updates with zero downtime for your actual end users, and then we'll also be digging into topics such as vertical and horizontal auto scaling based on usage on your system. So there's quite a lot of different topics we're going to be covering in today's video, and don't forget to hit that like button and to subscribe. So just to give you an idea of what the end result of this video will actually look like is you'll have a Kubernetes cluster similar to what is on screen at the moment. As part of this Kubernetes cluster, I will have a couple of deployments. So this first one that you see here, Hitman Web deployment, is a React web application, and it is serving static files that have been built as part of the React process. And then I've also got a couple of other deployments here. So Celery Flower is a way of viewing tasks that are currently being processed by your Celery workers. It's quite useful in a production environment if you're trying to diagnose or debug any errors with your Celery workers. You might have a task that's taking longer to run than expected. For example, I would recommend deploying Celery Flower as well. We also have a Celery worker deployment. So with this Celery worker deployment, as you can see at the moment, it's one of one pods, as you can see here. But this Celery worker deployment has a thing configured called a horizontal autoscaler. And what this means is if the CPU usage of a pod hits a certain level, then Kubernetes will start adding more pods onto this deployment. So an example is if you have a Celery task and all of a sudden you got 1 million requests to process a Celery task, you're going to need to add more Celery workers onto your worker pool to ensure that those tasks get processed within a reasonable amount of time. So Kubernetes has some really nice horizontal auto scaling features in there to do that automatically. And then there's also a concept called vertical auto scaling. So vertical auto scaling is whenever you increase the CPU or memory capacity of a specific pod, and then horizontal auto scaling is whenever you're adding more pods on. So you can always use a combination of both vertical and horizontal auto scaling strategies, which are quite useful, especially with Celery. I've also got a REST API deployment. So this is a Django REST project that I've created, but it doesn't have to be a Django REST project. It works with just a normal Django server. So if you're using a normal Django server configuration, the same Kubernetes configuration will also work for you. But that's the main parts of this deployment, and I'll just give you a quick overview of the GitHub repository. So I have a repository called Docker Celery, and with Docker Celery, there's 4 packages here that you can see here that are listed. These packages are Docker images, and a Docker image being built for the REST API, a Docker image built for Celery Flower, a Docker image for the Celery worker, and then a Docker image for the React web application. So each time I push to my main branch on GitHub, what will happen is Github Actions will create a new run job, and as part of this job, it will take the new code that is being pushed up. It will build a collection of Docker images. It will then push those Docker images to those repositories that I just shown you here. So these are Docker image repositories hosted on GitHub. You could be hosting your Docker registry on AWS, for example. It doesn't matter. It's all works exactly the same. And after it's pushed to those Docker registries, then Kubernetes is then notified of this update essentially by changing what are called the YAML file. So a YAML file is where the Kubernetes configuration is stored. So with each time I push to this main branch, the code will be built using Docker. These new Docker images will be pushed to my Docker registry, and then after that action is completed, then Kubernetes will update and roll the update across all the pods that are currently running, and also doing this in a way where the end user doesn't experience any downtime. So we'll be using a strategy called a rolling update strategy to avoid any downtime for end users. Start digging into some details around our Kubernetes configuration for our Django server. So you can actually view this YAML file yourself on the GitHub repository. Feel free to check it out while I'm explaining things through. I'll jump into the main sections of this Kubernetes configuration now. So here I am defining a container that is going to be based off of this Docker image. So this is the Docker registry that I previously mentioned that is on my GitHub account. You could have a Docker registry running on AWS, for example, or DigitalOcean. It doesn't matter. They all operate the same. But for your case, you'll be replacing this Docker registry with your own Docker registry, wherever that is hosted. So it's going to be pulling the Docker image from this Docker registry URL, and I'm then going on to perform a resource request. So Kubernetes has its own units of measurement for CPU and memory. So a CPU, one physical or virtual CPU core equals 1000 M. So in this case, I'm requesting 250 M of a CPU, which means I'm requesting a quarter of either a virtual CPU core or a quarter of a physical CPU core. It just depends on what your Kubernetes is actually running on. And then just below that, I'm also specifying the memory requirements. So I'm saying here that I'm requesting 100 M, which is 100 megabytes of memory. So this is going to be the minimum requirements for this container to run. But as I previously mentioned about the concept of vertical scaling is whenever you increase the CPU and memory requirements of a individual pod. So I'm saying here that this container has the ability to scale up to half a CPU core and up to 1000 megabytes of memory of RAM. So this is the minimum that it needs to run, and this is what it can scale up to. So here I'm also defining that I'll be exposing port 8000 for traffic to be forwarded to. And then Kubernetes has these things are regarded as probes. So there's two different types of probes available. There's a readiness probe and a liveness probe. A readiness probe is whenever you're performing a check on whether a container has successfully started, either from you manually starting the container or from say an update has just deployed to your Kubernetes cluster, and you're waiting to determine is the pod in a ready state after an update has deployed. So I'm saying here to Kubernetes that this Django REST container can be regarded as ready state if the following URL returns a successful GET request. So it's going to be making a request every 20 seconds to this URL on the container on port 8000. And once it starts getting a successful response back after making this request, then the container can be regarded as being in a ready state, and Kubernetes can determine that the container has successfully started. So where liveness probe varies is a liveness probe is more of an ongoing check. So if you have a pod that has been running for a long period of time and you're trying to determine is that pod still in a healthy state, you can define a set of conditions for that too. So I'm defining the same condition for my liveness probe, that if this URL returns a successful response or a successful response, then this container can be regarded as still being alive. So if this request starts failing, then Kubernetes will determine that this pod is no longer healthy, and then it will kill that pod and then create a new pod immediately after. So those readiness checks are really important for ensuring that whenever you're deploying an update, that there is zero downtime for your users, because you do not want Kubernetes to prematurely think that your pods are ready when they aren't, because if the pod is prematurely regarded as ready, and Kubernetes starts sending HTTP traffic to that pod, but it isn't actually ready to accept those connections, then you'll have a bunch of failed requests coming through. So it's a way of ensuring that whenever you're deploying an update, that you don't have any downtime, and Kubernetes can successfully determine when things are ready to start accepting HTTP traffic. So I've also up here defined a thing called a rolling update strategy. So what this is saying is that it will update one pod at a time, and it will keep doing that until all pods have been updated. So I've defined here that there is 2 replicas, so there will always be 2 pods running, and to avoid any downtime, it will update one pod at a time, and it'll wait until the first pod updates before updating the second one. And it's just a way of ensuring that there's always at least one container that is running, that is healthy and active and always accepting traffic, while the other is updating, and the 2 pods can swap over between each other, which is really great. Just below, I'm defining some environment variables. So environment variables are usually pretty simple. Just in this case, I'm using a thing called a Kubernetes secret. So a Kubernetes secret is just a way of storing any sensitive variables like database passwords, or like passwords of any type, for example. So I'm storing all my environment variables in the form of secrets, and these environment variables will be essentially injected into this container. And I'm defining environment variables such as like database details and some details around Celery. So that stuff's all simple enough. And then just down below, I'm defining a thing called a service. So a service is a way of facilitating HTTP requests being made to a deployment from an external source. So if you, in this case, I have a Django server deployment, and I want to allow external HTTP requests to be made to it, and a service facilitates that. So I'm saying that this service will accept traffic on port 80, which is the normal HTTP port, and I'll also accept traffic on port 443, which is where HTTPS requests would go through, and the target port for both is port 8000. So that's a quick overview of the Kubernetes configuration for the Django server. So after discussing the Django configuration for Kubernetes, I thought I'd just show you that very same deployment. So here I have the deployment Hitman REST API. If I click into it, you'll see that there's 2 pods currently running because we defined 2 replicas, and I can access it on this external endpoint. So this is the service that I had previously discussed, and I can accept traffic on port 80 and port 443. So if I just click into this, you can see that it is now accepting requests to my Django server. And if I go to /admin, for example, you can see I can just use my Django server as normal, which is great. I'll also quickly show you my Celery deployment. So I have Celery Flower and Celery Worker. So Celery Flower is a way of just viewing a kind of dashboard on your Celery workers and what they're currently doing. You can see here that I have one worker currently running at the moment that has processed one task, and that task has succeeded. And you can see here that I have my Celery worker running here. I have one pod currently running under my Celery worker deployment. If I click into that, you can see here in the logs that it is currently active, and it's it's in a state where it's ready to accept more Celery tasks coming in. So I just wanted to highlight the main things around the Celery Kubernetes configuration. So we've covered a lot of the main concepts within a Kubernetes deployment, which is great. So I won't need to go over everything again, but one of the main things I wanted to highlight is this thing in the Celery Kubernetes configuration called a termination grace period seconds. So with Celery has the ability to execute tasks, and tasks have a variable length and time where things can execute for. So if you have a task, for example, that takes 1 hour to complete, and you deploy an update to your Celery workers, you need to notify Kubernetes of how much time do you want to allow for a Celery worker to shut down. So you don't want your Celery workers to immediately shut down. What you want to happen is you want your Celery workers to finish processing what task they're currently processing and then shut down after that task has successfully processed. So this avoids the problem of Celery tasks going missing, for example. So this termination grace period seconds is telling Kubernetes how much time to allow up to before forcibly removing a Kubernetes pod. So this is providing a grace period for the Celery tasks, whatever ones it's currently processing, to finish up and process and then shut down. So we've allotted a lengthy time period for Celery to wrap up whatever tasks it's currently processing and to then shut down. So that was, I think that's just important to note. And then we have our readiness and liveness probe, once again, as previously mentioned. But in this case, because Celery isn't a HTTP server, we are performing a bash command to determine our readiness and liveness probes. So this bash command will just return essentially a boolean, true or false, and whether the Celery worker is currently in an active state and able to accept tasks. And the same concept applies again. And then just down here, we have to find a thing called a horizontal pod autoscaler. So in the case of Celery, you have a task, say all of a sudden you get 1 million task requests come through and you have to process them all of a sudden. You need to start adding more pods on to your Celery worker pool. And what we're defining here is that we will have a minimum of 1 Celery worker running at any given time and a maximum of 10 Celery workers running at any given time, but we're going to be scaling based off of the CPU utilization percentage metric. So if any pod goes over 50% or more CPU utilization, then Kubernetes will start adding more pods on in order to help with this kind of addition in demand. So this allows you to scale up and down in real time depending on the tasks coming through on your Celery pods. So that's an overview of the Celery worker configuration, and now I'll just give you an overview of how the continuous integration deployment works. So in the case of this project, I'm using a thing called Github Actions. So Github Actions is a service GitHub provides to facilitate continuous integration and deployment. So you can define say a task to perform tests for each build, or tasks on how to deploy a new update that's been pushed to your main or master branch. So this is all contained within the workflows folder. If I go to ci.yaml, this is my GitHub Actions configuration, and I have 2 jobs defined. So one job is to build the Docker images and push them to my Docker registry, and then the second task is to deploy the new Docker images to my Kubernetes cluster. So as part of this building and pushing my Docker images, you can see here that I'm running a script here called deploy sh, and this script is using these 4 environment variables. So this is a personal access token. So I'm using this token to grant permission to push to my Docker registry. This is my kubectl config. So the kubectl config is a configuration for connecting to your Kubernetes cluster. It contains stuff like the IP address to access the Kubernetes cluster, the password to access it essentially. And I'm also using a variable called build number, which will be the current build of this repository. So each time I push to my main branch, this build number increases essentially, and that's how I version my Docker images. And then I've also got here a React environment prod variable. So this will just contain a .env file, it's called, for React, and this will just be used as part of the React build process, so containing environment variables like passwords and stuff that the web application might need to access my API. And then here I have my deploy to Kubernetes cluster, so I'll give you a quick overview of that deploy sh script. So it's in the root of this repository, and you can see here that I'm performing all my Docker build operations. I build a container, so I'm specifying the location of the Docker file, and I'm building from the root of the repository, so it has access to all aspects of the code. So I'm building the Docker image, I'm tagging it with the version, so I'm using that build number to tag my Docker images, essentially, as previously mentioned, and then I'm pushing to my Docker registry. So my Docker registry is on GitHub, and I'm just doing this each time for my REST API, my React web application, my Celery worker, and my Celery flower. So after that has successfully executed, then what happens is this deploy to Kubernetes cluster kicks in. So essentially what happens here is that it will connect to my Kubernetes cluster, and after successfully connecting to my Kubernetes cluster with the right IP address and with the right password, what will happen is that it will go inside my Kubernetes YAML files. So you can see here that it's running this sed command, and it's running it against the REST API YAML file. So what it's doing is it's searching for the word version in my Kubernetes configuration file, and it's replacing the word version with the build number. So you can see here in all of my Kubernetes configuration file, so if I go to my REST API one, for example, I specify the word version in all caps. So as part of my CI CD process, what happens is that this word version essentially gets replaced with the build number. And then after that has actually occurred, then it will perform the operation of doing an apply. So this kubectl apply is what will alert Kubernetes of the changes to the configuration. So it will take this new Kubernetes configuration YAML file, and it will apply it to the cluster. So with each successful build on my main branch, it will take that build tag, replace the word version with the latest successful build, and then it'll apply it. And as part of this apply process, Kubernetes will perform all the updating, and it will deploy the update with zero downtime to the end users. So that's a quick whistle-stop tour of how the continuous integration and deployment works. And there's been a lot covered in this video, and there's a lot to digest, but I hope it's of help, and don't forget to like and subscribe. Thanks.